Well, hello everybody, and welcome back to another OpenShift Commons briefing. And today we're really happy and pleased to have Kyle Liberty and Paulo Paterno with us from Red Hat. We're going to talk about finding a workload balance and using cruise control for Kafka on Kubernetes. So I'm going to let them introduce themselves. They've got a wonderful presentation and a couple of deep demos to share with you today. And if you have questions, please join us in the chat wherever you are on Twitch, YouTube, or here in Blue Jeans, and we will get that relayed to our guest speakers today. So Kyle and Paulo, take it away, and looking forward to this talk.
Yeah, thank you very much, everyone. Thank you for joining us for this session. So let me introduce ourselves quickly. So I am Paulo Paterno. I am principal software engineer in Red Hat, working on the NQ Streams team. So I mostly work on Apache Kafka project and on Strimzi that we'll introduce in a little bit about running Kafka on Kubernetes. I am here with Kyle. Over to you, Kyle.
Hello, everybody. I'm with Paulo on the AMQ Streams team. And back to you, Paulo.
So let's see what we are going to see today during this session. We are going to have a kind of a quick introduction about Kafka for people who don't know about Kafka itself, and then how the Strimzi project that we work on today is really useful for managing Kafka clusters running on Kubernetes, so on OpenShift. I will cover these two main points, then I will hand over to Kyle about talking on cruise control and how cruise control is really useful for balancing Kafka cluster and how it's really integrated pretty well with the Strimzi. So let's start a little bit about talking about Kafka. Let's a brief introduction about Kafka. The Kafka definition is kind of changed over time, over the years. So Kafka at the beginning was mostly used as a messaging system. In the end, Kafka is a messaging system based on the publish-subscribe pattern, where you have some producer publishing messages on topics, and on the other side, consumers subscribing to topics and getting these messages. It's a distributed messaging system, but over time, so it's evolving as a standard de facto for doing some event streams processing, so stream processing in real time, event ingestion, things like that. In the end, we can say that Kafka is just a commit log. So you can think about these topics as files, as logs, where all the messages are appended by the producers. So all the events ingested by Kafka are appended by the producers, and then on the other side, they are read from the consumer. So since the beginning, other than to be a distributed messaging system, it's really scalable and fault tolerant. So it's scalable in the sense that we can add brokers, we can handle a lot of consumers on that side, we can add more producers, so we can handle high load traffic in order to exchange messages across clients. And it's even fault tolerant in the sense that if you have your Kafka cluster deployed with more brokers, but at some point, one or more brokers, it depends on the size of your cluster, go down, the Kafka cluster is still alive. The clients can still use the brokers in order to exchange messages through the topics. So it's really fault tolerant. But Kafka is not just about the brokers. So the core of the upstream Apache Kafka project is the broker itself for exchanging messages across clients, but it's more. So the upstream projects provide even library related to the producer and consumer API that you can use in your clients for using Kafka as a messaging system or an event streaming platform. There is even the Kafka Streams API, which is a kind of library that is on top of the producer and consumer API for doing some data streaming analytics in real time. So using a pretty simple DSL in order to do some filtering, mapping, and real-time processing on your data without using the low-level producer and consumer APIs. There is even Kafka Connect, which is today used for moving data through Kafka, so using Kafka topics across other different systems, like, for example, database. So maybe people know the project called Divisium, which provides some connectors for moving data from some database to the others. So for doing some CDC, so change data capture, for example, getting the change of a database into a Kafka topic and then moving this change to a destination database, for example. Another project is, for example, Mirror Maker, which is really useful when you want to mirroring your two different, so one Kafka cluster from one data center to another, for example. So it's not just the brokers, it's even more, it's an integrated ecosystem of different components. So this is what Kafka is today. Here you can see a kind of simplified Kafka architecture. So there is a kind of really simple Kafka cluster with just 3 brokers. I already mentioned that all the clients exchange messages using topics. The topic in the end is a kind of virtual object because Kafka it's using shards. So each topic is made by shards that are called partitions. And for example, in this case, I have one topic with 3 partitions, 0, 1, and 2. And then for each partition, we can have 1 or more replicas that are useful for fault tolerance, because I have more copies of the same partition on different brokers, so that if one broker goes down, I can use the copy of that partition on another broker. So this is why Kafka is really fault tolerant. So here we have these 3 brokers Kafka cluster with 3 partitions made of 3 replicas, and that the green ones are the so-called leaders. So each partition is leader on one of the broker, and the leader is an important role because a producer and a consumer can exchange messages through a partition, so sending and receiving messages through a partition connecting to the leader, while all the others are called followers because they are just copying the messages from the leader just for fault tolerance. From the consumer side, it's not even true, because today there is a new feature in Kafka where a consumer can even read from the closest replica, for example, so not really from the leader. But the base way as Kafka works is just connecting all the clients to the brokers where leaders live. From a scalability point of view, Kafka can scale because, for example, if you add more partitions, you can add a partition on a different brokers, for example, in this case. So we add the new broker, we have partition 3 added on the new broker, and you can scale even on the consumer side. So you can have more consumers getting more messages from more partitions, and it's all handled by Kafka. In the Kafka land, compared to the other traditional messaging system, we can say that the Kafka brokers are more dumb than the clients that are really smart. For example, the consumers taking information about where they are reading the messages. It's not done on the broker side. So for this reason, the Kafka brokers can even handle more loads and more consumers with more traffic. Talking about fault tolerance, as I already mentioned, it can happen that if a broker goes down, in this case, for example, with the 3 brokers in Kafka cluster, you add the partition 2 to be leader on broker 2. Broker 2 goes down, and the new leader of partition 2 is elected, for example, in this case on broker 1, and the application will just connect to the broker 1 and continue to exchange messages through partition 2, even if the broker 2 is down. When the broker 2 will come back again, it will happen that a new leader election will happen. The preferred leader will be again partition 2 on broker 2. So everything will back in the starting situation, as we saw maybe on the first slide. So this is how somehow Kafka is handling the scaling side, the fault tolerance side, and so on. But we can say that managing Kafka is not so simple. So let me say it's kind of hard. You have a lot of configuration to do on Kafka brokers. So if you can double check the Kafka documentation, there are a lot of parameters that you can set in the configuration. You have to operate your Kafka cluster. Operating your Kafka cluster means that you have to deploy your Kafka cluster, so having the same configuration on all the Kafka brokers. You have to set up the connection across brokers. Kafka today runs alongside the Zookeeper ensemble. So you also need a Zookeeper cluster where Kafka is storing some information, some metadata, like, for example, topics and partition information, the ACLs for the user, so the access control list, where the user can, the clients in general, can read and write topics on the cluster, information about who is the controller, what is the topology of the Kafka cluster, and so on. So there is one more thing to handle, which is the Zookeeper ensemble. That is going away, likely. The latest Kafka 2.8 release as a kind of a way for deploying a Kafka cluster, not yet in production, but you can use itself without Zookeeper, and it will be removed in the 3.x version that are coming. But for now, you have to deal with Zookeeper running alongside Kafka. So you have to operate your Kafka cluster. When you have to upgrade some configuration parameters, you have to respin the Kafka brokers again. So it's all in your hands, right? Even from a development point of view, it's not so simple for a developer to have handy a Kafka cluster running. You have to set up Kafka on bare metal, or even, I don't know, on virtual machine. So this is where even running on Kubernetes, on OpenShift, comes into the picture. Not just for production, but even for development, of course. So talking about Kafka running on Kubernetes, there is an easier way to do that. This is where the Strimzi projects come into the picture. So we could use the Kubernetes resources for deploying and handling our Kafka cluster. Kubernetes provides us a stateful set, secrets, config maps, and all the other stuff that you can write. So you can write your YAMLs, describe your pods for your Kafka brokers, the secrets with the TLS certificates, the config map with your configuration, but it will be always on your ends. So you have to handle all these YAMLs, you have to update these YAMLs for upgrading your cluster, etc. With Strimzi, you are getting an operator pattern approach. So you don't have a human operator handling your Kafka cluster, but you have an application. So in the end, an operator is an application, a pod running in your Kubernetes cluster that has the knowledge about your business. In this case, the business is Kafka, is running Kafka. So it has all the knowledge about how Kafka works, how upgrade Kafka brokers, things like that. With the Strimzi operator approach, you also use the way to extend the Kubernetes API. So using the so-called the custom resource definition, you can extend the Kubernetes API, adding some more custom resources. So other than having pod, stateful set, deployment, all the stuff that you have in Kubernetes natively, you also have a new Kafka custom resource, a new Kafka User, Kafka Topic custom resource, etc., even for handling Kafka Connect, Kafka Mirror Maker, etc. So this is what Strimzi is providing to you. So it automates the configuration of your Kafka cluster, describing your Kafka cluster through a Kafka custom resource, and the deployment. And then even the upgrade of your Kafka cluster. It also provides a built-in security in the sense that you can configure TLS certificates, you can encrypt connection with clients inside the cluster, so across brokers. You can configure authentication and authorization for your users. And we say that it's a simple user interface because you are to reuse your Kubernetes experience to handle a Kafka cluster. So if we dip a little bit more into it, we can see here how a Kafka custom resource looks like. So you have a new kind, which is this Kafka custom resource. And in the spec, you can just describe the configuration about your Kafka cluster, so the version, how many brokers I want, the configuration parameters, even the storage that can be the ephemeral one or even the persistent one. And you can describe even Zookeeper with at the same time the number of nodes, the storage, and more. It's just a really simple Kafka custom resource. In the first demo, Kyle will show, let me say, a more complex one. What happens when you create your YAML, you create your Kafka custom resource? The Strimzy operator, which is watching for the Kafka custom resource that you are creating, will just take care of it. So it will just translate this Kafka custom resource into creating some Kubernetes native resources. Like it will create a stateful set handling the pods for Kafka brokers, the pods for zookeepers, even the secrets for the certificates, for connecting from outside to the brokers, for intra encrypted connection in our cluster, even creating the config maps with the configuration, the persistent volume claim for persistent volume, for storing your messages in a persistent way. So the Strimzy operator is doing what you should do manually, but it's doing everything for you. So that if you update your Kafka custom resource in the config section, for example, and I don't know, tweaking some parameter, if this parameter needs the Kafka pods to be restarted, the Strimzy operator will take care of that for you. So it will start a rolling update one by one of the pods so that the clients will continue to use the Kafka cluster, because the Strimzy operator will restart just one pod at time. So it will take everything for you. The same if you use, I don't know, the Kafka Connect custom resource for deploying Kafka Connect or for Mirror Maker, but even for creating a topic or creating a user with the corresponding ACLs, you don't need to use the Kafka tools, but you can just define a Kafka topic, custom resource, a Kafka user with all the information about that. We will see a little bit more in the demo. But we are not out of the woods yet, because when you start to use Kafka, at some point your Kafka cluster becomes unbalanced because you are using maybe more partitions than the others. Like, for example, you are sending messages with some keys. The producer will decide what is the destination partition based on the key, for example. So you are sending more messages with the same key to a specific partition to a specific broker. So on that broker, for example, you have this partition getting a lot of messaging, some other partitions, and few partitions on the other brokers. So you have the first one getting more messages than the others. So you can have a poor performance for that. From a storage point of view, because you are utilize more the first brokers than the others. The network, you are not spreading the traffic, the network traffic across all the brokers, even about CPUs, right? So this is a scenario where you should use kind of better your Kafka cluster, because you are putting all the traffic, your load on broker 0 and broker 3 maybe, but not utilize it so well all the other brokers here. So this can happen even when you add more brokers, or brokers goes away and then come back. So this can happen. What does this mean? For example, if you start in this scenario where I have 3 brokers, I have a topic with 4 partitions, they are distributed in this way when the topic is created. Of course, we are getting 2 leaders on the same brokers because there is nothing that we can do. But at some point, we spin up a new broker. We would like to have the partition tree moved on the new broker, but it's something that doesn't happen automatically in Kafka. If in this scenario you create a new topic, then the partitions will be spread across all 4 brokers. But what you already have, it's just still running on the same brokers that you have before. So what you would like to have is just having the partition tree be moved on this new broker for spreading the loads across all the brokers, for using in the best way your CPU, network, storage on all the brokers that you have now. So the problem is, as I already mentioned, that this doesn't happen automatically. So this is another scenario why you can have unbalanced clusters at some point when you start adding more brokers, but you already have some topics spread with the partitions across the already running brokers. What we can do today for, we have to rebalance the cluster, right? It's not simple because it's a moving target, so brokers can come in and come away. You should optimize in terms of network, storage. So you should get some metrics. You need some metrics to know how the brokers are behaving, and then rebalancing and moving partitions in order to have more resources use it in more or less the same way across all the brokers. The old way today is to use a Kafka reassign partitions tool that is provided by the Kafka project upstream, but it's a kind of manual process. So you have to run this tool for getting in a JSON file how the partitions are distributed across your cluster. Then you have to specify in this JSON how you would like to move these partitions for rebalancing. And then you have to run this tool again for starting the rebalancing. It's a one-dimensional balancing because it's based just on storage. So you cannot get the rebalancing related to network and CPU and things like that. So we can do even better. And at this point, I would like to hand over to Kyle to introduce what you can use for having and for doing rebalancing even better using Kris control, and how Kris control is really integrated pretty well with Strimzi, so in the Kubernetes land. So handing over to you, Kyle.
Sharing my screen. Can everybody see my screen? Look good, Paulo?
Yes.
Excellent.
Yes.
So as Paulo said, we can do better. We can use cruise control. So cruise control is an open source tool developed by LinkedIn. It offers us fully automated rebalancing. And what I say by that, I mean cruise control constantly monitors the state of your cluster. It calculates and caches optimization proposals to best balance your cluster. It also provides a REST API for querying the state of the cluster and generating these optimization proposals and rebalancing your cluster based on these optimization proposals. Cruise control offers fine-grained resource tracking. So it can track the resource utilization of brokers and topics and even down to partitions. And cruise control also offers us multi-dimensional balancing. So cruise control can optimize rebalance proposals to target several different factors of a rebalance, including things like rack awareness or resource capacity and utilization for your resources like disk, CPU, and network I/O, and also per broker replica count, and many more, which I'll go into further detail later. So here I've just drawn a simple architecture of cruise control. As you can see, each broker runs the cruise control metrics reporter alongside it. It's run as a Java agent, and it'll collect raw Apache Kafka broker metrics. And it'll do a little processing, and it'll store those back into a Kafka topic. Now, these process metrics will be taken in by the cruise control load monitor and sampled over time to get a more accurate view of those raw metrics and build a model of the cluster, what it looks like at that point in time. And it'll pass this model to the analyzer, which is basically the core, it's the brain of cruise control. So cruise control will use the analyzer to build an optimization proposal of how to balance your partitions using the cluster model, which was produced by the load monitor, for optimally rebalancing your cluster. And we can also feed the analyzer a list of constraints with how we want the cruise control brain to come up with this optimization proposal. But we'll go into more of that in further slides. And as I said before, the cruise control also offers a REST API where we can query the workload state of the cluster and get detailed information on brokers, topics, and partitions, and also reviewing those optimization proposals that are generated by the analyzer, and then execute partition rebalances using the executor. So if we drill down more into the data that's kind of moving through cruise control, so we have, as I said before, we have a metric reporter, the cruise control metric reporter, running alongside every broker in our Kafka cluster. And these are collecting raw Apache Kafka broker metrics, which you're probably familiar with. Information like the partition size, the broker CPU utilization of that broker, the topic bytes in and out, and then the message rate. For this at the partition level, the topic level, very detailed. So cruise control will sample these raw metrics to get kind of a better view of these, a more accurate accounting of these data points. And you can see, we get the broker idea where those raw metrics came from. We get a better measure of the CPU utilization, the disk usage, and the network I/O as well. So these metrics, they're read and processed from these raw metrics, and we can produce these kind of samples, these metric samples, at the partition and the broker level. And they're used by the load monitor to get an accurate sound accounting of the data surrounding the brokers in your cluster. So here's kind of just a diagram showing kind of how that data is aggregated and put together and processed. So we have our metric sample, which we saw in the previous slide, which we can customize the sampling interval. We can also customize the reporting interval, just depending on what our needs, how fine-grained we want those metrics to be. We also can customize time windows to basically create snapshots of these metric samples that we take. And we specify how many snapshots we want the analyzer, the brain of cruise control, to use to come up with a cluster model. So we can basically set up these numbers so we can get the past hour of traffic of cruise control, or the past day, past week, month, year. It just depends on how quickly your Kafka cluster is changing or moving, and so we can just customize that to meet your needs. So just to reiterate, a specified number of snapshots, which the user will specify, produces a precise and up-to-date estimation of what the cluster looks like at a given point in time. And it's used to create a cluster model. So the cluster model is basically just the workload data of the cluster resources. So this is kind of a very simple example of what a cruise control cluster model will look like. So you can see if we had a 3-broker cluster, broker 0 is 24 replicas, 24 leaders. You see how much disk that broker is using, the CPU utilization, the network I/O. But there is much more detailed information we can get from this cluster, like down to the topic, and even as far down as the partition level as well. And this cluster model will be used by the analyzer to basically simulate partition movements and decide how to best rebalance the Kafka cluster, given constraints we give it. And as I alluded to before, the Cruise Control REST API, it's there for the user to basically query information about the cluster, like the current broker partition load, the Kafka cluster state, the optimization proposals, what they look like, the information about them from the analyzer, and also executing those optimization proposals using the executor, and many more. So like Kafka and the other Kafka components like Mirror Maker and Connect, Strimzi offers integration with Cruise Control, this optimization, this partition balancing tool. So Strimzi will deploy Cruise Control and auto-configure it. It'll also roll all your Kafka brokers to include the Cruise Control metric reporter agent for collecting those fine-grained metrics. And Strimzi, like all of his other components, offers a simple user interface for interacting and controlling your Kafka cluster, all in one centralized place, the Kubernetes CLI and custom resource. So I've expanded on Paulo's diagram for the cruise control part. So using the Kafka resource, we will declare our cruise control configuration for our cruise control application. The Strimzi operator will see that description in our Kafka resource, and like it deploys the Kafka cluster, it'll deploy the cruise control application alongside everything else. And it'll also roll all your Kafka brokers to include the cruise control metric reporter, so it can connect and gather that data. We also have a Kafka Rebalance Resource, and this is used for interacting with the Cruise Control REST API I was talking about earlier. So we edit, and basically we can, using the Rebalance Resource, we can tell Cruise Control to generate optimization proposals based on custom constraints, and then execute the rebalances based on the optimization proposals that Cruise Control creates for us. So here's just a closer look at the same Kafka resource that Paulo showed earlier, only with the cruise control configuration. So here we see the things we want to focus on here in the next slides are the cruise control goals section, which is in the cruise control config. Note this is, you can put the majority of cruise control configurations here in the Strimzy Kafka resource as well, and also the broker capacity section here, which I'll show in the next couple slides. So, as I said before, we have constraints that we can give the analyzer to come up with optimization proposals. So these goals or constraints cover many different dimensions of a partition rebalance. Like, for example, rack awareness ensures that replicas are spread across different racks. We have, we can specify the replica capacity goal, which ensures that no broker contains more than a specified number of partitions. And then there's also resource capacity goals, which make sure that broker resources don't exceed a specified threshold. So we give cruise control these goals or constraints, and the optimization proposal we get from cruise control is promised not to violate those constraints that we give it. So, and note there's two different types of goals here that we can feed our cruise control configuration. There's hard goals and there's soft goals. So hard goals are goals that are constraints that must be satisfied by cruise control when it's generating optimization proposals. They can't be violated. So if we tell cruise control we want no more than 2 replicas on each broker, the optimization proposal will either give us an optimization plan which will meet that restriction, balance our partitions so that each broker only has 2 replicas. But if it can't meet that restriction, and it's a hard goal, cruise control will not generate an optimization proposal. It'll say, no, we can't do that. We also can provide soft goals for cruise control, which is, maybe we have constraints that aren't as important. Maybe the disk usage per broker isn't that important. And so we can specify as a soft goal, and cruise control will do the best job it can to satisfy that constraint. But if it can't meet it exactly, maybe it's at, 80%, of your disk, but you specified 70%, but it's okay because you said it's a soft goal. So cruise control offers kind of a lot of customizable flexibility there when setting up these constraints. Also specified, you start on that Kafka custom resource, we have configurable capacity limits, which are used by the cruise control goal restrictions. So here we can specify the exact amount of disk that we want each broker to be limited by, or the CPU utilization or the network throughput. So if you look at kind of this diagram here, if we specified a CPU capacity like this line here, note that the CPU capacity, the CPU usage bars right here will not exceed that line. So we specify this in our Kafka resource, and the goals will use that to respect that when cruise control is coming up with an optimization proposal to balance our cluster. So we've looked at the Kafka resource in detail. Now it's time to look at the Kafka Rebalance resource. So remember, the Kafka Rebalance resource is the interface to the cruise control API, so we can communicate with it. And it focuses mostly on just rebalancing the cluster. So here we can see that we have a Kafka Rebalance resource. It's an object just like we have a type Kafka resource. We have a type Kafka Rebalance resource, and we specify a goals section here. Remember those constraints we were talking about in the previous slides. So the goal list we provide here, it will override the default goal list we specified in the cruise control configuration in the Kafka resource. So maybe generally you want cruise control to be balanced in a certain way, but maybe you have a sudden need to balance your cluster. Maybe you have different new constraints, and it's just a one-go balance. So you can specify a new list here and pass it to Kubernetes. The cluster operator will communicate with cruise control and have cruise control create a partition rebalance optimization proposal based on these restrictions that you've put in this Kafka Rebalance resource. So the Kafka Rebalance resource goes through a series of states. So it starts, when you create a Kafka Rebalance resource, it starts in this proposal pending state. That just means cruise control is calculating an optimization proposal based on those goals you've given it. And once that's complete, cruise control will it'll tell the cluster operator. The cluster operator will pass this information back to the Kafka Rebalance resource, and it'll move to the proposal ready state. That just means the optimization proposal was generated by cruise control and it's ready to go. And until the user specifies that it looks good and they want to rebalance, cruise control will wait. But once you're ready, you can set it, you can annotate the Kafka Rebalance resource. The cluster operator will talk to cruise control and it'll start rebalancing your Kafka cluster, in which the rebalance resource will be in the rebalancing state. And once it's finished, once it's all done, the rebalance is complete, the Kafka Rebalance resource will move into the ready state. So you can basically track the life cycle of a rebalance through this kind of state machine. So we track kind of the state of the Kafka Rebalance resource through the custom resource status section. So here we have the second state, the proposal ready state. So that, remember, that just means that cruise control has come up with an optimization proposal based on the constraints you've given it. And it also feeds us some nice information about that rebalance. So this is a dummy example. So the partitions removed in this example didn't have any data, so there's 0 data to move. But in a real life situation, you'd have the exact number of data you need to move. You have information like how many leader partitions are being moved, and the replica movements. And they also provide, cruise control also provides a balancedness score, which is basically their view of how balanced your cluster is. And as we see here, before we've executed this rebalance, before we tell the Kafka Rebalance resource we want to move forward with this rebalance, we see that cruise control thinks that our balance score is lower than what it could be, based on the cluster model that it's created, its understanding of the cluster at that point in time. And after cruise control has done its work, you hope to have a somewhat even distribution of load across your brokers. It's probably not ever going to be perfectly flat, but it's going to be in much better state than what it was before, based on your constraints. But anyway, enough talking. Why don't I dive into let me dive into introducing Strimzi, and then we'll dive into a second demo for cruise control. All right, so in this demo, the first demo, I'm just going to show you how to deploy a Kafka cluster and what kind of the nice interface Strimzi provides for that Kafka cluster and how we can manage it. So I already have the Strimzi operator deployed, and I'm just going to show you the custom resources that we provide with Strimzi using custom resource objects. So let's take a look at those. So as you can see, we have these Strimzi objects based on custom resource definitions. So we have a Kafka Resource object that's used for creating Kafka clusters, and Kafka Topic objects for creating Kafka Topic. So let's just make sure that our cluster operator is up and running. So we can just double checking, making sure that it's there. So now that we see it's ready, why don't we just deploy our Kafka cluster by sending it a description of a Kafka custom resource like this. And while that deploys, let's just take a closer look at that description of the Kafka, that Kafka custom resource, Apache Kubernetes. So here, Paulo's already showed most of this. There's a little extra I've added here, which I want to highlight. So as you can see, we have our Kafka resource. We're running Apache Kafka 2.7. We could have put any Kafka version here that's specified by supported by Strimzi, and it would have deployed a Kafka broker of that version. This cluster just has one broker. We also have a listener section, which is basically Bootstrap addresses for accessing our Kafka cluster. We have one Bootstrap address that allows insecure traffic, and one Bootstrap address that it requires TLS client authentication. And we could have put another listener here to allow traffic from outside the Kubernetes cluster here as well. But I haven't included here. We have our Apache Kafka broker configuration we can put here, and it'll be automatically applied to all the brokers in the cluster. We have some JBOD storage, 10 gigabytes per broker that's persistent. And we also have, because Kafka still has a hard dependency on Zookeeper, we have to deploy a Zookeeper cluster alongside Kafka. We declare it here. We have one Zookeeper instance with its storage. So these customizations here are not exhaustive. We could have added also other configurations for things like metrics and security and other Kafka components. Let's just see that this was deployed. Oh, so we can see that our Kafka broker has been deployed. So is our Zookeeper instance. So it's done its job. And with this cluster, there are a few things Strimzy gives us for free out of the box. One of those things is security. So, all communication within the cluster is encrypted and authenticated by default. And now we also get automated configuration management, which Paulo talked about earlier, where we make basically one change to our Apache Kafka broker configuration in the Kafka resource, and it's applied to all of our brokers automatically. So now that we have our Kafka cluster running, let's create a Kafka topic. So we can do a little more interesting things. So I've created a Kafka topic just like that, the same way I created a Kafka cluster using a Kafka Topic resource. But let's just take a closer look at what I've just passed Kubernetes. So here we have, our Kafka Topic object, which I was talking about before. We want this topic to have 3 partitions and 1 replica per partition, and the Apache Kafka Topic configurations can be listed here, and it'll be taken care of it'll be taken care of by Strimzy for us. And note that it's named my topic, which will be later. So look at. So we've passed Kubernetes a topic resource right here. And the topic operator, which we deployed with our Kafka cluster, will read that resource and create a Kafka topic in our Kafka cluster just like that. And as we talked about earlier, we have a simplified user interface. So to interact with our topic, see that it was created, we can use the Kubernetes CLI like this and search for our Kafka topics. So we can do like this. So as we can see, we have our other Kafka topics, our consumer offsets, but we also have my topic, which we just declared and I showed you. We have 3 partitions and we have 1 replica per partition, just like that. So now that that's been created, let's go ahead and create a Kafka user that can write to this. So we'll, again, I think you get the idea. We'll apply another YAML file that describes our Kafka resource, our Kafka user resource. Let's take a closer look at that. So there's a few things I want to focus here. One is our, authentication field right here. So this will allow our Kafka user to be recognized by the Kafka cluster. Here we're specifying we want our Kafka user to use TLS client authentication. We could have used other authentication methods like Scramshaw. We also define an authorization section here. So our Kafka user will have privileges to interact with the topic we've created. Here we use access control lists for accessing our topic. For reading to my topic, as you can see here, as well as writing to my topic we created in the previous steps. And then the last thing I want to focus on here is the user quota section, which allows us to limit how much our user can read and write to the brokers in our cluster. So here we can limit the producer byte rate and the consumer byte rate as well as the CPU utilization limit as a percentage of time used by the client group that this user is a part of. So just like our Kafka topic resource, we've created a Kafka user resource. And this will be used by the user operator, which we deployed originally with our Kafka cluster. And that will create a Kafka user in our Kafka cluster. And we can interact with our Kafka users just like we interact with our Kafka topics and other objects using the Kubernetes CLI like this. So as we can see, my user, which we just showed you in the previous step, has been created. and it's authenticated to the cluster using TLS client authentication, and it's ready to go. So now that we have those set up, we have our topic, we have our user. Let's start writing to this topic. So I'm just going to go ahead here and deploy some producer and consumer apps. So let's take just a closer look at what I've deployed. So the core things I want to highlight here is that we are using the secure Bootstrap address that I showed you in the Kafka resource. So this Bootstrap address is so clients can access Kafka, but it only allows authenticated traffic. So these producer and consumers have to be authenticated to my topic, which we created in the previous step, by using the Kafka user, my user, which we created in the previous step. So these environment variables will hook up this producer and this consumer down here to the Kafka user we created. So we'll be able to read and write to our Kafka topic, my topic. So those have probably been deployed by now. So let's just make sure that they're writing and reading messages accordingly. So if we go here and we look at the logs, they spit out the traffic to logs, producer, and we'll follow that. So as we can see, we have our Kafka producer. It's authenticating to our cluster, and it's writing messages. Now let's check on to our consumer. Make sure that it's reading appropriately. And we can see that our consumer on the right side is reading those messages. It's authenticating to cluster and reading those messages from our Kafka cluster appropriately. So note that no other clients that are using the secure Bootstrap address will be able to read and write to this topic without being tied to our Kafka user. And we can nicely, interact with our Kafka topic and Kafka users and other objects using the Kubernetes CLI. But anyway, that's the end of this demo. Let me move on to the cruise control demo to show you some more interesting rebalancing magic. So I've recorded this part of the demo to kind of reduce the wait times, because cruise control can take some time to generate proposals. So let me go into that. So here we're just going to show you, how to use Strimzy cruise control integration. So far, our demo has just used one Kafka broker. So this raises concerns with performance and fault tolerance, as Paulo's told you. And we can even see that our topics partitions are piled up on one broker here. So you can see that all our, broker 0 is where all our partitions of our cluster are right now, which isn't good. So we're going to want to scale our Kafka cluster by editing our Kafka resource like this. So here we can just change the replicas field right here to 3, and that will scale our Kafka cluster to 3 brokers. So we'll see that, as a similar pattern to the last demo, we have our Kafka resource, and the cluster operator will read that Kafka resource, the description we provided, and it'll create a Kafka cluster based on that description. So we'll have 3 Kafka broker pods when this is finished. So let's just give it a second to let the cluster operator scale our cluster, and let's just check right here, see if it's complete. And as you can see, we have 3 Kafka brokers in our cluster right now. Before we only had 1, but we have one problem, and that problem is that all the partitions are still on broker 0, as Paulo was talking about. These partitions aren't automatically spread amongst our brokers. So we need to do a little more work. And basically, to get around this issue, as we talked about, we can use cruise control. And we can deploy cruise control in a similar fashion to how we deployed other components, like Kafka, the Kafka topics, Kafka users, the entity operator, by editing our Kafka resource. So let's go ahead and do it here. Here, just edit our Kafka resource. We'll just put a simple cruise control field right here, just empty. Now, this will just basically, be read by the cluster operator, like all the other changes, and it will deploy the cruise control app alongside our cluster. And then it'll also roll all our Kafka pods to run the cruise control metrics reporter along each broker as an agent to pick up those metrics that cruise control will use. So let's look at the pods to make sure that the cruise control has been deployed. We can see cruise control is right there. So that's been deployed. The brokers have already been rolled. They're up and running and they're ready to go. So now we need a way of interacting with the REST API for the cruise control REST API. And so doing that, the way we do that is using the Kafka Rebalance resource that I was talking about in the slides. So let's go ahead and create one of those like this, applying a YAML file. And this resource will act as the medium for cruise control. Take a closer look. So here, as I showed in the slides earlier, we just have a Kafka Rebalance resource. The purpose of this resource is just for generating optimization proposals based on restrictions that we pass cruise control and executing partition rebalances based on those optimization proposals that are produced. So here are the goals, restrictions we were talking about earlier. Like we have the CPU capacity goal, which will make sure that the generated proposal will keep CPU utilization for any broker in the cluster under a given threshold. And so, see, we create our rebalance resource. Will be used by the cluster operator, to interact with the cruise control REST API to create an optimization proposal. And once it's complete, it'll pass it back to the rebalance resource where we can take a look and approve it if it looks good to us. So let's just take a closer look at the status section. We can see that right now cruise control is creating a proposal for us. Remember, the rebalance resource follows kind of a state machine. So right now it's a pending proposal. Cruise control is hard at work. And now we can see cruise control is completed. It's, optimization proposal. So we're now in the proposal ready state. So, and it also provides some nice information, as I showed in the slides, more detailed information about that rebalance. And if it looks good, we can annotate that resource. And that will tell cruise control to execute the partition rebalance based on the proposal that's passed back to us. So we can see now that since we've done that, the Kafka Rebalance resource is now in the rebalancing state. So Kafka cluster is currently rebalancing all the partitions across our brokers. And once that's complete, we'll be in the ready state. So our cluster has been rebalanced. So we're all good to go. So we passed our 4 states. Our cluster has been rebalanced. Now all we need to do is just check to make sure that our partitions aren't all on broker 0 anymore. And as we can see, they're spread out now. There's still some partitions on broker 0, but we also have some on broker 2 and broker 1 as well. So our cluster has been rebalanced. I'm using cruise control and Strimzy integration, and that's the end of the demo. So what's next for cruise control integration with Strimzy? We're looking at securing the cruise control API with authentication authorization. Right now, the API is only secured by Kubernetes network policies, but you can get around that by using Kubernetes port forward or pod execing. So this will secure that further. Intrabroker debalancing as opposed to interbroker balancing. So this will support balancing data not only between brokers, but between disks of the same brokers. And then also we're looking to support cruise control's ability to change topic replication factors. But that is the end of our presentation. I hope you've enjoyed. Now we'd like to open up for some questions. That's all right.
So great, Kyle. That's just amazing, and a lot of rebalancing magic there. So this has been a pretty wonderful conversation and demonstration of the power of cruise control. And it's also I'm really thrilled to see yet another end user donating an open source project. It totally makes sense that with the popularity of Apache Kafka, that a tool like this is absolutely necessary, and it's wonderful that it's come out of LinkedIn, with huge numbers of Apache Kafkas to manage, and we all know brokers do die, so that must be really painful. I'm wondering, you're both Red Hatters, have you seen a lot of adoption of cruise control at Red Hat customers? Have you been with Strimzi deploying it, or is this, how new is this all to the universe?
So, Paulo, do you want to take this one, or shall I?
No, go ahead.
So we've introduced this integration, I believe, last year, and I don't know about Paulo, but what I've heard, it's our customers' favorite tool to use to speed up their clusters. But that's what I've been told. Paulo, I don't know what you've heard.
Well, I'm not sure about customers. We had this feature for tech preview for a long time. Now it's GA, right? Yeah, to be honest, I guess that customers are just playing with this right now because the integration works pretty well in Strimzi, but we want, as Kyle already mentioned, we want to add more in order to have authorization, authentication. So the security side, I don't think we have customers using this in production, but for sure we are customers trying this in order, to move to production as soon as possible.
Oh, awesome. So where does cruise control in the pantheon of foundations and everything live? Is it in Apache? Is it in CNCF Sandbox? What is the plan for the cruise control, or is it going to stay just in the LinkedIn repo and be something that we link out to?
I think it's, well, yeah, it's still in the, it's not part of the CNCF or anything, or Apache. It's still kind of a standalone GitHub repo. I see kind of the popularity, it's getting more popular as I see more people, more companies are starting to contribute to cruise control, which I'm assuming that's meaning, it's getting more adoption, and maybe once it gets more traction like that, maybe we'll see it move to an open source foundation.
Yeah, I think that to me, that would be, once we have the integrations that are in your roadmap for Strimzi, it would be almost a natural thing to nudge them towards getting into a foundation and maybe more open governance and oversight, because along with the security, having that extra panache or whatever, the extra seal of approval helps our customers adopt things as well. So, and other people's customers and folks in production. But it is, you talked about, Paulo, in the beginning, getting out of the woods. I mean, this gets us a huge step forward in managing, rebalancing all of these Kafka workloads and stuff. So that it's pretty amazing. What do you see as the timeline for some of these things that are on your roadmap? I know that's a terrible question to ask engineers and other folks, but is this something that's coming in with, perhaps the next 6 months or so, or is it sooner?
Well, I guess, but Kyle can be more precise than me, that the authorization and the authentication is coming really soon, because actually it's Kyle working on this kind of feature. Maybe the other stuff I don't want yet to commit to have them in 6 months, but yeah, for sure the first one is coming. Maybe the topic replication factor could be later. The last one should be the one about rebalancing inside a Kafka broker, right, Kyle?
Yeah, as you said, the API authentication authorization is coming. That should be in the, hopefully not this pending release that's coming out in a week of Strimzi, but maybe the next release once we thoroughly test it. Intrabroker balancing is hopefully coming soon too. Maybe we'll have that in the next 2 releases. The work there isn't too hard. The changing the topic replication factor is not trivial. It's going to require a lot of work and a lot of testing. So like Paulo, yeah, I totally agree. It's going to take a little more time to get that ready for customers and people in general using Strimzi.
Yeah. So we're at the end of our hour, so I want to respect people's time and really thank you guys for giving us a great tour de force on explaining Kafka, Strimzi, cruise control, rebalancing, and all the theory and practice behind it. So I really appreciate the update, and we'll definitely have you back for the next release. And we definitely want to hear if you're a customer and you're playing with this, or an end user that's playing with cruise control, any feedback you have, we'd love to hear it. So please keep in touch. And Kyle and Paulo, where is the best place for people to reach you guys in terms of community interactions?
Well, for sure, we have a Strimzi Slack channel on the CNCF workspace. There is a dedicated Strimzi channel because Strimzi is under the CNCF Foundation. So this is the best channel for reaching us, even the user and devs mailing list in Strimzi. And you can find a lot of information on strimzi.io, documentation, and there is really a lot of blog posts about Strimzi. Even on Twitter, you can reach us. So there are a lot of ways, I guess, that it's really simple to engage with us.
Perfect. All right, guys. Well, thank you for everything today. I'm going to let you all go, and we'll have this uploaded shortly. Thanks to Bobby Kessler and Chris Short, who are our producers. And we'll talk to you again tomorrow with another talk on data science from Audrey Resnick. So if you're listening, join us tomorrow, same time, same place, OpenShift TV for OpenShift Commons. Thanks, guys.